Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 6 of this course on machine learning for earth system science. We are continuing the module 1 which is on spatiotemporal statistics. So, today we are going to talk about extreme events. So, like you can consider this as an extension of the previous lecture which was on anomaly events. So, the concepts we are going to cover today are extreme values and quantiles, return levels and return periods, and spatial and temporal coherence of extreme events. So, let us begin with the definition of anomaly which we already covered in the last lecture. So, anomaly is basically just the deviation of an observation from its long term expected value. So, suppose the observation is at any given location and time is x of st and its climatology is mu of st, like we had discussed in the last lecture that this might be the spatial or temporal climatology also. Now, if so by subtracting them what we get is y of st. Now, if y of st is positive, then we call it as a positive anomaly, and if it is negative we call it as a negative anomaly. However, if the anomaly is above a particular threshold, let us call it as nu, then we may call it as a positive extreme. Similarly, if it is a negative anomaly and it is below some particular negative threshold, then we can call it as a negative extreme. Now, what these threshold are, nu, nl, etc., that is a it's again it's subjective and context dependent. Like it is sometimes people use the double standard deviation as a measure of these nu and nl, but that is not strictly necessary, and it is possible that in some of the situations that one of the extremes may not make any sense, like for example in case of daily rainfall. So, daily rainfall like positive extreme makes sense, like if we have a very large quantity of rainfall, we call it as if there is 100 millimeters of rainfall at a given location on a given day, we can call it as a positive extreme. But there is no negative extreme to be defined in this case. I mean, rainfall can never be negative, and if it is 0 rainfall, that simply means a day in which it did not rain, there is nothing extreme associated with it. So, in that case only positive anomaly makes sense. But if we are considering, let us say annual rainfall, then both positive and negative anomalies may make sense. Now, to understand that, let us look at the daily rainfall time series of Kharagpur for in the months of June to September for this period of 15 years from 2000 to 2014. So, the total number of days here is so there are 15 years. In each year from 1st June to 30th September there are 122 days. So, the total number of days we are dealing with here is 15 into 122, which is 1830. That many data points we have, and at each of those days we have these measurements of rainfall. So, why did we choose this particular period June to September? That is because this is the monsoon season, and most places in India including Kharagpur receive at least 80% of their annual rainfall during this monsoon period only. Okay. Now, the mean rainfall here, the daily mean is 9.13 millimeters per day. So, as you can understand that on some days it is the rainfall is above that mean, and some which means a positive anomaly, and on some other days it is below that mean, which is the negative anomaly. So, now if we like put the threshold at 9.13, so like these days which have these are the days which have the positive anomalies, and these are the days which have the negative anomalies. Now, let us say we plot the histogram of this of these values. Okay, so like you can understand that on most of the days the values are actually quite low. So that is why it is 0 or close to that. So, we see that it is the small values which have the maximum frequency, and higher the values are, the lower is the frequencies. Okay. In fact, like it is quite rare for any day to have, let us say, more than say 40 millimeters of rainfall. Now, on this kind of a histogram, let us put the value of mu, the climatology. So, that as we already said, that value is 9.13. So, here like we have drawn this red vertical bar to indicate that these are the like negative anomaly incident events, and these are the positive anomaly events. Now, apart from mean, let us also calculate the standard deviation sigma. So, like let us say that we have some value of standard deviation about say 12 or something like that. So, or maybe slightly higher, maybe 15. So, mu plus sigma is the value somewhere here. So, here we have put another red bar, and similarly mu plus twice sigma, that is like we have put another red bar here. So, like we can say that all values that are beyond any of these thresholds, we can consider them as the extreme events. So, like the standard practice is to choose mu plus 2 sigma as the cutoff or the threshold, the NU as we are saying, for the extreme positive extremes. So, like every day in which the rainfall has been above this particular threshold, which is say something like 40 millimeters, all those days will be considered as extreme rainfall days. Okay. So, but you can see from this distribution how rare those extreme rainfall events are. Most of the days are actually below the that is, they have negative anomaly on, like only a small number of days actually have positive anomaly, and then among those positive anomaly days, a very minuscule fraction of the days actually have the extreme rainfall events, if extreme is to be defined in this way. If extreme is defined is this way as mu plus 1 sigma, then the number of anomalies, I mean extremes, will of course be slightly higher. So, similarly we can define some other thresholds also for extreme. Now, that brings us to another concept for defining these extremes, that of percentiles or quantiles. So, so quantile is basically, so suppose we have in some kind of a probability distribution, let us say something like a PDF. So, like if we draw like a figure like this, let us say this is some kind of a probability distribution. Okay. So, what we can do is we can we can actually divide this range of values. So, like on the x axis what we have is basically the support set. Now, this and on the y axis we are having the PDF. Now, we may choose to divide this support set into certain sectors like this. Those sectors may be at like at any regular intervals. So, each of these sectors, these are known as the quantiles. Now, there are certain special ways of defining quantiles. So, for example, there are quartiles, like I may divide the whole thing into 4 parts. Let us say this is the first quarter, then this is the second quarter, the third quarter and the fourth quarter. So, these can be called as the first quartile, the second quartile, etc. So, these are the quartiles. So, note that quartile is different from quantiles. Similarly, we can also define percentiles. So, percentile is something which you are all familiar with in case of like because the results of these competitive exams like GATE or IIT JEE etc. are often expressed in terms of percentile. So, percentile is when you divide the whole supports into 1000 bins or 1000 sectors like this, and so you can say that percentile is a special case of quantiles, just like quartile is a different case of these percentiles. Similarly, there are deciles and things like that. This is related to the concept of median. So, median is like you have a range of values, and the median is the exactly that value, such that 50% of the values are above it and the other 50% of the values are below it. So, similarly, just extending the concept of medians, we get the concept of quantiles, right. So, like in this case, again we use the idea of quantiles, especially percentiles. So, let us say that let us consider the 99th percentile. That means 99% of the days will have lower value of rainfall than a particular value. So, in this case, the 99th percentile, or if instead of calling it as the 99th percentile, you can just call it as 0.99. So, like you can say that with 0.99 probability, the rainfall on any given day is going to be less than a particular value. So, if you do an analysis of these values which we considered here, you may find that in this data set, if you do an analysis of the values, you will find that that cutoff value is 69 millimeters. That is, there are only 1% of the days in which the rainfall is more than this 69 millimeters. In other words, if you consider any random day, any out of those 1830 days, if we choose any day at random, there is only 0.01 probability that the rainfall on that day will exceed 69 millimeters. Okay, and its actual frequency out of those 1830 days is 18 days. So, as you can understand, roughly 1 by 100. Similarly, the 90th percentile is 25 millimeters. 90th percentile, that roughly means that there is 0.9 probability that if you pick up any day at random, the rainfall in it is going to be less than this threshold of 25 millimeters. And it turns out that there are actually 183 days in which the rainfall has exceeded this 25 millimeters. 183 out of 1830. So, that is just 10%. Similarly, we can define the 0.75 or the 75th percentile, the 50th percentile, and so on. And 50th percentile, as you can understand, is just the median. So, there are 915 days in which the rainfall is more than it, and another 915 days in which the rainfall is less than it. And it turns out that the median value is 3.4 millimeters. The interesting thing to note here is that the median rainfall is 3.44 millimeters, while the mean rainfall we had earlier seen is much larger, it is 9.13 millimeters. That means what? That means it is a very skewed distribution. In case of Gaussian distribution, we know that the mean, median and mode, all of them coincide. That is, there are what a mean or the is the it's like the expected value of the Gaussian distribution is also the most frequent value, and like you can expect that the number of samples which will have lower values is roughly going to be equal to the samples which will have higher values. That is why Gaussian distribution is called the perfectly symmetric distribution. But in this case, clearly that this distribution is highly asymmetric. You can see that it's the low values dominate, but there are some very high values also, like you can see some values like 80, 100, etc. In fact, the maximum value is 154 millimeters. So, how high is that compared to the mean? So, it's like we can say that in most days or on at least 50% of the days, the rainfall is actually below 3.4 millimeters, but there are some very rainy days also which have pulled the average from 3.4 to all the way till 9.13. Okay. So, this is a typical example of a like a long tailed distribution. So there are some probability distributions have there are some probability distributions which are symmetric like the Gaussian, and then there are some which are skewed or asymmetric like this one. I mean, this histogram you can consider to be the PDF of some probability distribution. So you can understand that this is a like it's a skewed distribution, but it is also a long tailed distribution. What do I mean by that? That means there are various tail events, that is which are very far away from the where the bulk of the probability mass lies, but like say values like 154 and things like that, they are very far away, but they still have some probability mass. So that is this is like called the tail of the distribution. So the like as you can see, the this thickness of the histogram, this vanishes at 40 millimeters, but it's not that higher values don't occur. In fact, a value as high as 154 millimeter also occurs. That's why we say that it's a distribution with a very long tail. Okay. Now many geophysical variables have this kind of a long tailed property. Now, as I said that there are only 573 days in which the rainfall is above the mean, that is they have some kind of positive anomaly, while the remaining days, so this 573 out of 1830, this will be roughly about 30%, maybe 31% or something like that, and the remaining 69% of the days are having a negative anomaly. That means the negative anomalies are much more frequent than the positive anomalies. In other words, that means that most of the days are dry and the bulk of the rainfall is concentrated in a few wet days. Okay. So that actually we like for those of us who have first hand experience of the Indian monsoon, we will understand that that is actually like we can corroborate with our daily experience. We know that even during monsoon season, it's not that it's raining all the time. There are many days in which it does not rain, but there are some days in which it rains heavily and makes up for that. And like in there is also the hypothesis that one of the impacts of climate change is going to be this effect is going to be more and more accentuated. That is, we will see a larger fraction, an even larger fraction of these dry days or negative anomalies, and an even but the days in which there will be positive anomaly, the number of these extreme events are also going to increase. Now, this brings us to a concept of return period. So, suppose an event happens today. So, suppose there is something very strange happens today. Let us say there is suddenly 100 millimeters of rainfall. So, you can understand how rare that is. So, now once it happens today, I may think that this event happened today, so much rainfall happened today in Kharagpur. The last time this happened was, let us say, 20 years back or 35 years back. These kinds of statements we see being made when something very unusual happens, and corollary to that is when do we expect it to happen next. So, like the general idea is that the common events may happen soon afterwards, but the rare events because they are rare, it's unlikely that once they have happened, we may think that it's unlikely that it will happen again. It's something like saying that lightning does not strike the same place twice. So, the return period is defined as 1 by p, where p is like the event probability. So, this is something like it follows from this 1 by p, it's something that follows from the geometric distribution, which is related to how many times I must toss a coin before with bias p before it gives me a head. Okay. So, now if we consider a 90th percentile event, the probability of such an event happening is 1 minus 0.9, which is 0.1. Why? Because in 90% of the days the value observed will be less than that 90th percentile value, right. So, like the probability of such an event happening, which is at least as heavy as the 90th percentile, it is only 0.1, and the return period is 1 by 0.1, which is 10 days. So that means that once this kind of an event happens, 90th percentile event. So in case of that Kharagpur rainfall data set, that 90th percentile was 25 millimeters. So like it's like saying that if on a given day yet there is 25 millimeters of rainfall, we may expect such a thing to happen again after 10 days. Okay. However, this kind of a thing actually does not happen. What happens is that extreme events are often clustered in time, and the differences between the two 90th percentile events is most likely not going to be 10 days as was calculated here, but something like it can be much smaller. So here is actually a histogram of the difference between successive like 90th percentile events like that. So you can see that once again the bulk of the distribution lies, or the bulk of the probability mass actually lies in this range, say 1 to 8 or something like that. So most that means in vast majority of the cases the return period, the actual return period between two 90th percentile events is much less than the expected return period. That means what? That means that these kinds of extreme events tend to be clustered in space. So we can actually calculate this as follows. So let us say, let us just calculate that tomorrow there will be a positive rainfall anomaly. So that means more than 9.13 millimeters of rainfall. The probability of that is of course 0.31. So we have seen that in the data there are some 573 or positive anomaly days, which is 573 out of 1830 is 0.31. So there is 31% chance that tomorrow there will be a positive anomaly. But if I already know that today there has been a positive anomaly, then the probability that tomorrow there will be a positive anomaly goes up to 0.46. So that means positive anomalies tend to be clustered in time. If today there is a positive anomaly, most likely tomorrow, I mean it is likely that tomorrow also there will be a positive anomaly. That is how these kinds of things work. So the concept of return period, I mean it is not actually very practical. It does not actually tell us much. I mean like it only gives us an expected value of when that event is likely to return, but typically it is not like that. Now if we like similarly, instead of considering the positive anomaly, if we consider the 90th quantile or 90th percentile event, so the probability of that is of course 0.1 just by definition. But if you know that today a 90th quantile event has happened, then the probability that such an event will again happen tomorrow shoots up to 0.25. That means like from 0.1 it has gone up to 0.25. So again it shows like the same effect, that these kinds of events are usually clustered in time, and not only in time but they may be clustered in space also. So if one location has a positive anomaly, usually its surrounding locations also have such an anomaly. So like an analysis of the data shows us, if Kharagpur has a positive rainfall anomaly on any day of monsoon, on 60% of the occasions its surrounding locations also have a positive rainfall anomaly. So in the absence of any further information, the probability of having a positive anomaly, as we have seen, is just about 30%. For nearing locations it might be slightly more or less. But if we know that on any given day Kharagpur is having a positive anomaly, then that probability shoots up from 30% to nearly 60%, which is a huge rise. Similarly, if you consider the 90th percentile rainfall events in Kharagpur, which we saw is some 25 millimeters of rainfall or something like that, it turns out that 45% of those days are accompanied by 90th percent rainfall in the neighboring locations also. Similarly, and not only that, in 60% of those cases the neighboring locations have 80th percentile cases. Okay, so that this shows the spatial coherence of these kinds of extreme events. And now this brings us to the concept of quantile plots. So here basically we are comparing the like the different various quantiles of two different distributions. So let us for example here like we are considering the rainfall distribution in March at a given location, and here we are considering the rainfall distributions in July at the same location. So you may be surprised to see the values of -2, -1, etc. I mean, how can rainfall be like negative? But so what they have done is they have in fact it's not rainfall, sorry, these are temperature. So what they have done is they have standardized it, which means that like basically they have removed the anomalies. So here we can see that like this -2 is something like the lowest value, and +3 may mean the may be the highest value. So here what they are doing is that they are plotting the different quantiles in March against the same quantile in July. So the basically they have plotted something like the 50th percentile in March versus the 50th percentile in July, or the 75th along the x axis we may have the 75th percentile in March, which may let us say that it is this value 2, and on the y axis we are plotting the corresponding 75th percentile in July, which is something like 1.1 or something like that. So as you can see, the if we consider the higher percentiles, then March in March it is higher, but if you consider the lower percentiles, then in July it is higher. So that means like if like if you consider the let us say the hottest day in March, which is something like the 99th percentile or something like that, that is very high, that is that may be something like 3. But in case like the corresponding value in case of July might be in fact it's not 3, it is something like let's say 2.7, right, the end of this distribution somewhere here. But the corresponding value, the highest value in July is actually much less, it's like something like 1.8. But the it's quite the reverse if you consider the lower end of the spectrum. If you so it's like saying that the hottest day in March is hotter than the hottest day of July, but the coldest or the colder days of March are cooler than the colder days of July. So this this kind of a QQ plot, it enables us to match the nature of these extreme events at different locations or at different time points as this case is. So like this sets up a very background for a further discussion of these extreme value statistics. So like we actually the various probability distributions which we are familiar with, they don't work well when we are dealing with exactly with the extreme values, and in the next lecture we will actually see how we can define specific probability distributions for these extreme events. So the key points to be taken away is that the extreme event thresholds, they may be defined at locations. The thresholds may be absolute, like something like mu plus 2 sigma, or relative, which is the defined quantiles. The extreme events tend to be spatially or temporally clustered, and the severity of an extreme event is characterized by its return period. So with that brings us to the end of this lecture. We will continue our understanding of these extreme events in the next lecture as well. So till then, bye bye.